In the preceding examples for testing the mean of a population, we knew the population standard deviation. In most cases, however, the population standard deviation is unknown. As such, the population standard deviation may be estimated by the sample standard deviation S. For these cases, the t distribution is used as the test statistic. The formula for computing the t statistic is shown on this slide. It is computed by first getting the difference between the sample mean and the hypothesized mean. Then this difference is divided by the standard error of the mean. The standard error of the mean is computed by dividing the sample standard deviation by the square root of the sample size. This concept of using the t-distribution for testing the mean is similar to the concept we encountered in Chapter 9, where we learned how to compute a confidence interval estimate for the mean of a population whose standard deviation is not known. Now let's consider an example for testing a population mean when the population standard deviation is unknown. The McFarland Insurance Company Claims Department reports the mean cost to process a claim is $60. An industry comparison showed this amount to be larger than most other insurance companies, so the company instituted cost-cutting measures. To evaluate the effect of the cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims processed last month. The sample raw data is reported on this slide. At the 0.01 significance level, is it reasonable a claim is now less than $60? In setting up the hypotheses, the key words are, is it reasonable a claim is now less than $60? The keyword less than translates to mu less than 60. This calls for a left-tailed test. Since the population standard deviation is not known, we select the t-distribution as the test statistic. The significance level was set at 0.01. In obtaining the critical t for carrying out a left-tailed test, we need to determine the degrees of freedom, which is obtained by sample size minus 1. In the problem, it is 26 minus 1, or 25. We use the t-distribution table to obtain the critical value, given a significance level of 0.01 and the degrees of freedom 25, as shown on this slide. The critical value is negative 2.485. The critical value is negative because the test is left-tailed. In other words, the area of rejection is on the left side of the distribution. On the previous slide, we determined the critical statistic to be negative 2.485. The next step is to compute the t statistic using the formula sample mean minus the population mean. We then divide this difference by the standard error of the mean. The resulting computed statistic is negative 1.81. We locate this value on the distribution and find where it lies with respect to the critical value. The computed statistic lies within the fail to reject the null hypothesis region. Therefore, we can't reject the null hypothesis at the 0.01 significance level. The translation of this statistical conclusion is that we have not demonstrated that the cost-cutting measures reduced the mean cost per claim to less than $60. The difference between the sample mean and the hypothesized mean is likely due to sampling error. Here's another example of testing the population mean with an unknown population standard deviation. The current rate for producing 5-amp fuses at Neary Electric Company is $250 per hour. A new machine has been purchased and installed that, according to the supplier, will increase the production rate. A sample of 10 randomly selected hours from last month revealed the mean hourly production on the new machine was 256 units, with a sample standard deviation of 6 per hour. At the 0.05 significance level, can Neary conclude that the new machine is faster? So the keywords in this problem are, can Neary conclude that the new machine is faster? The word faster translates to mu greater than 250. This calls for a right-tailed test. Since the population standard deviation is not known, we select the t-distribution as the test statistic. The significance level was given at 0.05. Since there were 10 observations in the sample, the degrees of freedom is 9. Using the t-distribution table, looking up degrees of freedom of 9 and a significance level of 0.05 for a one-tailed test, we obtain a critical t-value of positive 1.833. Next, we apply the formula for computing the t-statistic. Using the information on sample mean, the population mean, the sample standard deviation, and sample size as stated in the problem, we obtain a computed statistic of 3.162. The computed statistic is greater than the critical statistic. In other words, the computed statistic lies in the reject the null hypothesis region. We will therefore conclude to reject the null hypothesis. This means that the average number of units produced by the new machine, based on the data, is more than 250 per hour.